So now we'll go into chapter 5, which is dedicated to building Bayesian networks. This is actually the longest chapter in your book. There are three kind of topics in this chapter. The first is dedicated to the set of queries that you can pose to a Bayesian network or to a probabilistic graphical model more generally. And the second and the bulk of the material in this chapter is a number of case studies on how to build Bayesian networks for various applications. And then the third part is dedicated to a few practical issues that come up when building Bayesian networks. This includes, for example, how do you deal with the situation when you have too many parents per node and the CPTs gets large, or also how do you better understand the significance of the numbers, and that touches on sensitivity analysis. So it's all material of a practical nature. And what we'll do next is first start by talking about queries, and that's going to be a substantial part of the discussion because there are 4 classes of queries. We're going to go over them in some detail and how they relate to each other, and we'll also talk a little bit about their complexity. But we're going to talk about their complexity at a high level and intuitive level. That will help you appreciate what's going on, but also some of that discussion will play a role later when we talk about algorithms for these queries. So we'll start with that. They'll eat up most of the first hour, and then we'll go over the case studies and cover more material as we go on. All right. So and just again, before I start, let me say that there are 2 ways to building Bayesian networks: the machine learning way and the other. Machine learning is coming later, so we'll talk about learning these networks from data later. But today we'll talk about the other method, not from data or not exclusive from data. And you're going to see there also there is 2 ways. One of them is to synthesize Bayesian networks from other type of information, or to build them by hand, which gives you really more insights into how these things work. All right, so we'll talk about the queries, and we will start with the first query, which is called probability of evidence. And we will be using this particular network for our illustrations. This is known as the Asian network. It's actually available in the literature, and we will be using screenshots from a system called SAM-IM. I mentioned that before. That's was actually built here by my group, and it's available online, and you can you will actually use it in your homeworks. I should also mention that it already comes with a whole bunch of small tutorials. So everything we're going to talk about today, the queries and so on, there is short tutorials on these online. All right, so here's the first query, the probability of evidence. And what you have in this case, you have a Bayesian network, and you have some partial variable instantiation. In this particular case, we have x yes and d no. These are these 2 variables. And I want to just compute the probability of that combination, which happens to be this. And this is what we would call the probability of evidence. Typically, bold E, big bold E, is used for evidence. And therefore, you would see this a lot in the book to represent the probability of a particular piece of evidence. And this evidence was a variable setting. Sometimes you have evidence of a different nature, like here. Suppose that I want to know what is the probability that X is yes or D is yes. Okay, that's a disjunction. Almost always in this setting, in probabilistic setting, when you say evidence, people talk about a variable instantiation. This is this variable has this variable has that value, and so on. Now this is a little bit different. And interestingly enough, if you look at tools out there for example, Bayesian networks, they don't directly handle something like this. They only allow you to enter evidence in its simplest form, which is partial variable instantiation. So what do? Suppose you have a tool that only handles evidence, as I showed on the previous slide, which is setting variables to values and finding the probability of that. And now you want to compute the probability of a disjunction like this. How do you do that? What you can do is use the technique that people call auxiliary nodes. You can add an auxiliary node to your model that capture this particular event and reduce this kind of a query to the previous kind of query. Look how it works. And this is actually pretty general. You can use it in many other contexts. So the idea is, what I'm going to do is, I'm trying to compute the probability of a disjunction over X and D. I add this new variable E, right? I add it to the network and make these two guys the parents and make this variable behave like an OR gate. So if you look at the CPT for this variable, you can see that as long as either X or D is a yes, then the probability here is 1. When both of them are no, the probability is 0. And I don't have a picture for this, do I? Okay, I don't. So what you do in that case is you add basically this node as a D here and make these two guys the parents and simply assert the value of E being true, right? And you will basically get the same effect, right? So you can look here that E equals yes is then equivalent to X being yes or D being yes, right? Again, you add an auxiliary node to your model. We're going to see the same technique actually to handle soft evidence by emulating a noisy sensor, similar technique. Okay, so this is the probability of evidence, whether it is a partial variable instantiation or whether it's a more general Boolean sentence. Now, this works for small Boolean expressions. If you have complicated Boolean expressions, this may not be the effective way. Later, actually, we'll study more sophisticated techniques for computing the probabilities of arbitrary Boolean expressions, which are based on more sophisticated logical techniques. All right, so that's the first kind of a query. And the second class of queries is what people call prior and posterior marginals. Let me first actually show you that visually before I show you the equation. So what's going on here is I have the model or the Bayesian network, which, by the way, we have how many? 1, 2, 3, 4, 5, 6, 7, 8 variables. So this network is specifying a distribution over these 8 variables. But what people are interested in typically is the distributions over individual variables. So is the person a smoker or not? What's the result of the positive X-ray? 11% yes, 88.9 no. These are called marginals, marginals over single variables. You can also have a marginal over 2 variables. It's not shown here. So you look at these 2 variables. They have 4 possible states. I give you a distribution over those 4 possible states. And there is the prior marginal, which is this, where I don't have evidence. And there is what people call the posterior marginal, where in this case I do have some evidence. So the fact that this is here, it's actually red on SAM-IM. That indicates that I know that the positive ray, that the X-ray came out positive. And here I'm saying that I know that D is negative, right? So I'm asserting this as evidence. If you're using the tool, you just go to these boxes and click on them. And you're asserting the values of these variables. So if you look previously, for example, you would have these probabilities. And then if you assert the evidence on these 2 guys, these probabilities got updated. So we had prior marginals and posterior marginals. And if you want to look at it more technically, what's going on here is I do have a joint probability distribution over the variables x1 through xn. And now I'm trying to compute the marginal over a subset of the variables, x1 through xm. All right, so this is a subset of that. And the way you do this is basically use this equation. So these are the variables I'm trying to compute the marginal over. These are the other variables, the remaining ones. I basically go over all their possible values and add up these quantities. You can see it visually if you're looking at the joint probability distribution. You're basically just compressing that table. We're going to look at it more later. Okay, so now we have the probability of evidence. That's one. And now we have a prior and posterior marginals. In fact, from a complexity point of view, both of these get lumped together. So in some sense, we really did basically one query from a complexity point of view. And now we're going to have 3 more. 2 are covered in your book, and the last one is not, because it's more recent. It was introduced after your book was published. And so 1 group, 3 more, and they, as you see, they fall into 4 different complexity classes. In fact, you will see the difficulties of these as we go on. Okay, so here's another. Okay. So I'm not going yet to the next one. I want to tell you about how to do a virtual evidence first, before we go to the second group of queries. Remember virtual evidence. I come to you and tell you I have an evidence that doubled the odds of something, right? How do you do that? Again, the tools do not directly give you support for this. And as you saw from the lecture on soft evidence, we said that we can emulate that kind of evidence using a noisy sensor. In fact, we wrote an equation that said if you want to double the odds of something, then use a noisy sensor that has the following false positive and false negative rate. We're going to use this now. And what I'm trying to do here is, this is the variable E that I introduced, which represents the disjunction of these 2 guys. And now I want to say I have evidence that doubles the odd of that statement. The statement was, I think X is true or yes, or D is yes. Okay. So the way I'm going to do it is, I'm going to introduce this auxiliary variable. This is more like a sensor, right? This is the sensor that could trigger on or off. And when someone comes and say, I have evidence that doubles the odd of E being yes, I want to emulate that by saying, okay, the sensor V triggered. And the only thing that's left now is choosing the CPT for that particular sensor. And if you know the CPT for this, because 2 values, the CPT for this would have 4 parameters, right? But only 2 independent. And these 2 are the false positive and negative rates. So here it is. The evidence that I have on E being yes is that it doubles the odds. I know that I need the following. I need 1 minus the false negative over false positive to be 2. If you unfold these guys and look at it from a CPT point of view, this is the probability that the sensor will not trigger even though E is yes, correct? And this is the probability that the sensor triggers even though E is no. I just want to make sure that that's equal to 2. Okay, here's one choice of a CPT. There's multiple of them. But this particular CPT for V satisfies this property. If you take these numbers, plug them in here, you're going to get a 2. Right? Again, you could have chosen something else. And here it is in action. Look what happened here. This is before I got the evidence. And if you look at the prior marginal over E, it's this. E is yes, 47.56, and so on. Now, the evidence comes in that the odds of E being yes doubled. I simply go ahead to this guy and say triggered, correct? Look what do I get for now the posterior marginal over this variable. Here it is, right? You can confirm that the odds have actually doubled. If you compute the odds of this guy, posterior odds on ES, and the prior odds, you plug the numbers, you actually get it too. So in fact, what is intended happened in this particular case. It's a very nice way of handling soft evidence and Bayes factors using these sensors. All right, so now we'll go to the next query. Again, think of everything we did so far is in one group. We called it probability of evidence of different types, simple, Boolean, then as we see here, soft evidence, and then we also looked at prior and posterior margins, all basically in some group, same group from a complexity point of view. Oh, now we're going to do what is known as the MPE query. Right? This has been receiving a lot of attention recently. And what we're doing here is the following. It's kind of an optimization query. So let's say these are the variables in my Bayesian network, x1 through xn, right? And I have this particular evidence. I observed the value of some of the variables. Look what I want. There is now a posterior distribution, right? The probability of these variables given the evidence now got updated. What I'm interested in, the specific instantiation of these variables, x1 through n, that has the highest probability. So if you think about it, the Bayesian network, let's say, have 15 variables. There are multiple settings of these 15 variables. I'm looking for the one that has the highest probability. And that's what I'm giving you back. So I'm giving you variable instantiation. That's called the MPE. Here's an example, again, from SAM-IAM. And again, you can play with these. That network, I have this evidence that this guy is yes, and this guy is also yes, right? And I ask for the MPE. I think the MPE icon is right there. And here's the MPE window. It's basically saying, okay, here's the variable setting that has the highest probability, and it's also giving you the probabilities up there, how much that is, right? And of course, you may have multiple MPEs, multiple solutions, multiple instantiations that have the same probability. We're good? Okay, this is MPE. This is the map. And map is very similar to MPE, except we don't optimize all of the variables. You choose a subset of the variables, and you say, I want the most likely state of these particular ones. All right? And those are called the map variables. So this is the set of all variables in the Bayesian network. We're picking a subset of them, M, and I say, optimize those particular M. As I said, these are called the map variables, and this query is known as the maximum a posteriori hypothesis, MAP. Now, obviously, MPE is a special case, right? If I take M to be all variables, what am I get? MPE. Then in that case, you say, so why do I have two of them, and why am I giving them different names? Why don't I just talk about this guy? And the reason is, as you'll see, anybody wants to guess? Complexity. There's a big difference between the complexity of this or that. If you restrict M to be X, and therefore you're doing MPE, that's a much simpler problem. Okay, let me say two things about approximating these. In fact, I skipped something on the previous slide, which is, let's say MPE. I'm trying to find the most likely state of all of these variables, correct? Now, one of you may say, wait a minute. If you know how to get marginals over variables, then you can do MPE, right? So go to every variable and see what is the most likely state, right? So did we have that somewhere before? I have to, okay, so you say like, okay, MPE, look at this guy. So no is more likely, pick that. Here, yes is more likely, pick that, and so on. If you actually do that, go to each variable, look at its marginal, and pick the highest value, and put them together, you do not get an MPE, right? You've got to be careful here. That only works if the variables were independent, but doesn't work in general. And in fact, I think this was trying to illustrate that point. Choosing values with maximum probability in this particular example with this evidence give you this variable instantiation, but that's actually not the MPE in this case. The MPE doesn't have S equals yes. The same thing for map. You may think if you're trying to optimize a subset of variables, then do MPE, right? Optimize all of them, and then choose the subset of it that corresponds to map variables M. Also, that doesn't work. And I think there is an example coming up. So in this case, I'm doing map. Here's the evidence. And the map variables are A and S, these two guys. And the map tells me that this variable instantiation has a highest probability, and it's actually giving me the exact probability, which happens to be this, right? So it found an instantiation of these two variables with this as its probability, and it's claiming that this is the highest you can do for those two particular variables. If you look at the previous example, here's the MPE that we got, right? When we optimize over all variables. If you project this on the map variables, you get this. And that's actually not as good as what we found, right? that basically has this particular probability, and the real map is this guy with that particular. So in this case, it wasn't that bad as an approximation, and people sometimes use this as an approximation, right? You solve MPE and project on the map variables, and then you're good. Now, in your book, there is a situation that's discussed where the two correspond to each other, where the MPE itself, if you take it and project it, you get a correct map. But I'm going to skip this and talk about the last query that we have. All right, so once more, 3 so far. There's the group of probability of evidence, prior and posterior marginals, all one group. And then there's the MPE, and then there's map, and this last one is called the same decision probability, or the SDP. And now you're going to see a change in style of the slides because this material is not in your book. This is, I think, 7 years old, this particular query. And it actually happens to be the most difficult computationally when we look at the complexity classes. But actually very interesting. In fact, when I explain it to you now, you're probably going to be wondering, wait a minute, why did it take so long for this query to be formulated? And to illustrate this query, it comes out in decision making, particularly when you're trying to collect information. So here's an example we're going to look at more later about 3 tests that you can do: urine, blood, and scanning tests that are meant to detect whether an artificial insemination procedure was successful. And what's going on here with a network like this is people use these usually like what we call a classifier. That is, once you collect the evidence on these or some of them, you compute the posterior on that, and then you check usually against a certain threshold. Let's say in this case is 90. So if it's, let's say, greater than or equal 90, you say yes, pregnant, otherwise it's not. And in this particular example, let's say that the scanning test came out to be false, and now the posterior is 40%. That's less, so the decision is no, right? That's a classical usage. So what is this query? The query comes out like this. When you're in a situation like this, there's something known as the stopping criteria in decision making. What do I do? Do I accept this negative decision, or do I go get more information? Because remember, there's 2 more tests that you can do. You can still check the urine and the blood. And the question again is, do I go get more, or do I stop? Now, you can imagine this is almost a never-ending question, because usually there is always more information you can gather, and now you have to actually decide. That's called, again, the stopping criteria in decision making. When do I stop and make a decision? And of course, if you decide to say, no, let me go get more information, there is the secondary question, which is called the selection question, which is, what information do I get? So let's say you're going to get you decide you want to get more information. What do I do? Is it the urine or the blood, right? Okay. So we'll just look at the first one, the stopping criteria. Here's the query, right? That's where this SDP query comes in. What is the probability that my decision will stick even if I get more information? So I have here 2 tests to do, and then you ask yourself, what is the probability that I will not change my mind even after I get these 2? Now, if that probability is very high, then you say, it's not worth it. I'll stop, move on, right? My decision is robust. If it's low, then the other question becomes relevant. That's basically the query. Same decision probability. And as you'll see, it is an expectation, some kind of an expectation. And in this particular case, if you do compute the SDP, it ends up being 78.7%. Now, depending on the application, this may be or may not be good enough. And remember, anytime you're going to compute the SDP, you have to tell me what variables you're thinking about measuring. So it's with respect to a secondary set of variables. In this case, those would be those 2 guys, all right? Because you may have like 10 variables that you didn't measure yet, and you're thinking about 3 of them. You say, what is the SDP with respect to these particular 3? Let me show you one more example with respect to this guy. In this case, I did the scanning test, but the scanning test came out negative, actually. Positive, sorry. And then look what the probability of pregnancy, 99.83. And that's now a positive a decision, right? Positive. If you compute the, so then the question is still, what's the SDP with respect to these two guys? In this particular example, it turns out to be 100%. Provably, there's no way. Doesn't matter. So don't even waste your time. And you can have a lot of examples where it's like 99.999. It's like very robust. You know, it's very unlikely that you change your mind if you measure these two particular variables. And just one last slide to just get a sense of what's going on here. Let's look at this Bayesian network, which is known as a naive Bayes structure. So this is the decision variable. I already observed this guy, and the probability of D given this evidence is this. The threshold is 50%. So at this point, I have a positive decision. And now I'm thinking about whether to measure these or not. So I want to compute the SDP. Look what's happening with the SDP. I didn't write the equation for you, but here's how it looks. What you're really doing is you're saying, look, two variables, right? Those are the ones that I may measure. They have four possible states. These are the four possible outcomes if you go and measure them. For each outcome, what am I doing? I'm doing two things. First, I'm saying, what is the probability of the decision variable given that outcome? So in this case, it's 95. And what decision would I make in that case? That would be true, above threshold, right? And you look at all cases. So there are four possible outcomes. Three of them would lead you to a positive decision, and one would lead to a negative decision, right? What do? If you want to compute the same decision probability, you look at all possible outcomes that lead to the same decision, and you add up their weights. What's happening here? What is the probability that I will see this outcome? What's the probability that I will see that outcome, and so on? Right? This is the equation. This is not how you compute it. You can't do it this way. It will blow up. Right? But conceptually, it's saying, I'm measuring these three guys, 8 possible outcomes. Let me look at one by one, which one the decision will stick, and add up their weights. Pretty simple, right? It's an experience. Once more, it's amazing. It was missed. This is only 7 years ago, right? So actually, we introduced this query, and there was already one PhD thesis dedicated to this by one of our students, Suming Chen, who's currently at Google, who did his thesis dedicated to the subject. And it's now being used also for doing what people call in machine learning feature selection. Because there's the second question is, okay, I realize that my decision is not robust and would probably likely change if I observe more. What should I observe later? And you can use this for that in the following sense. You can say, I want to observe the guy that once I know its value, my SDP becomes very high, in the sense that further observation are unlikely to change that. So you want, in a way, if you have like 10 features, you want to choose the 3 that if you measure next, make the other 7 redundant or useless. I will give you, the next slide, a sense of the complexity of these queries. It's important how difficult they are. Now, I'm going to show you a picture that has complexity classes in it. And I'm assuming you're going to recognize one of the classes. The other 3 may be new to you. And then I'm going to give you intuition on what these classes are, and you'll see how. All right? Let's first look at the classes. So I guess most people have heard of NP and NP complete problems, right? Example of that is satisfiability. How many people have heard of the class PP? Okay, couple. Okay, it gets worse. NP to the PP? Okay, same person. PP to the PP. Okay, they're funny names. They have interesting meanings. We're going to see. So look what we're going to do. These are the complexity classes. As you know, there is NP and there is NP complete. What does NP complete means? The hardest problems in NP, right? PP complete, the hardest. Again, what does that mean? That means if you solve an NP complete problem, or you have a box that can solve that, then you can use it to solve all other problems, right? That's in that class, and similarly. So MPE happens to be complete for this. It's basically hardest problem in this class. Marginals, hardest in that, and so on. And so as you're going up, things are getting complicated. So all we know from this is relative difficulty, right? that this is the easiest, the guy up there is the hardest. What is missing from this picture is the intuition of behind these classes, right? What's going on? Now, here's how we're going to break into the intuition here. It will allow us to do this and allow us to serve another purpose. Every complexity class has what people call a prototypical problem, the exemplary problem in that class. So if you say NP or NP complete, what is the exemplary problem? Satisfiability, right? That's the guy that represented in the most abstract and nicest way. Each one of the other classes have also its own. So what I'm going to do next is run quickly over the prototypical problems of these classes. And you're going to see they're all variation on SAT. Very nicely, easily explainable, right? Now, what's the purpose of that? We're going to get two things out of this. One, we're going to have a feel of these classes. But second, believe it or not, one of the ways and state-of-the-art ways for solving these problems is by doing reductions to these prototypical problems. Because if you've studied algorithms in complexity, you see one of the techniques is that if I have a solver for SAT, right, which is NP-complete, and then you have another NP-complete problem, one way to solve it is to reduce it to SAT and use the SAT box on that. And that's actually been around for a long time in complexity as a theoretical exercise to reason about the difficulty in problems and so on. But with SAT, it's become quite practical, the last decade at least, and so on, where people really do try to solve NP-complete problems by reduction to SAT. Now this is actually propagating to these other classes as well. And later, we will show you some of the state-of-the-art techniques which are based on this. So let's do a quick run over these guys, and you will actually see now, I hope when I do this, you're going to see this claim I made in the first lecture about how logical techniques from a computational point of view could be critical for probabilistic reasoning. Now you're going to see it for real. All right. First, the names of these guys. Okay, SAT is the nicest one. And then this guy's called maj-sat, e-maj-sat, maj-maj-sat. These are the names of the prototypical problems. And they're all problems on Boolean formula, believe it or not. But as we go up, you're going to see that it's Boolean formula plus some more. And again, this is before we go to these, the idea is the reduction is if you have this that's complete for this class and you have a solver for it, if you have another problem there, then instead of building a solver for that problem y, you reduce it to x, use the x solver to get an answer to x, and you can convert that as an answer to y. Once more, the reason for this is if you have boxes for maj-sat, then you can do marginals. If you have a box for e-maj-sat, then you can do, remember what that is? Map. If you have a box for maj-maj-sat, then you can do SDP. All right? And in fact, all of these reductions exist already. All right, folks. Okay, here's SAT. So now I'm not telling you much. Here's the Boolean formula, A or B and not C. Here are all of the variable instantiations. And what does SAT say? Is there a satisfying instantiation? That is there a world that makes this guy true? The answer is yes, and here's the guy. And by the way, as you know, in these things, we're talking about decision problems whose the answer is just yes or no. But we're going to look at a couple of questions. Now you're going to tell me, wait a minute. Really, I can use this to do. I can do this to do MPE. Yes. In fact, there is a variation on this called maj-sat, where not only do you find a satisfying assignment, but one that satisfies some properties. That's where the reduction happens. But let me show you the second, because now you say, wait a minute. I mean, the thing that you're probably still struggling with intellectually is, where are the numbers? How can I do stuff on symbolic equations and end up solving a numeric problem? You're going to see this in just a second. Okay, here's maj-sat. Maj-sat is majority sat. It's a variation, and the question is same input, Boolean formula, but instead of saying, is there a satisfying assignment, I'm saying, are the majority of instantiations satisfying? Right? You know what the difference is between the two? One guy will stop once it finds a solution. The other guy will not. I want to make sure that the majority of them, so it's counting. It has to count them effectively. And PP is usually referred to as the counting class. And once you know how to do counting, that's the same kind of computational power of doing probabilistic reasoning. So in this case, the answer is no, because I have 8 instantiations. Only 3 of them are satisfying, and then no, the majority is not satisfying, and the answer is no. Now, let me give you 2 variations on this. And those are the ones that people actually reduce to when they do probabilistic reasoning. And then I think when I do the variations on this, it becomes very clear to you why really this is powerful enough to do probabilistic reasoning. One of them is called model counting. So instead of a yes-no answer, I want a real count. It's called sharp-sat, where I tell you how many satisfying assignments. Give me the actual number 3, right? And even the other variation, and this is the one that I'm going to show next, where people do actually reductions, it's called weighted model counting. So what I'm doing here is, not only I'm counting them, but I'm giving a different weight for each instantiation, and I want you to add up the weights of the satisfying instantiations. So before you said 3 of them, in this case, no, you're going to tell me this guy is 0.04, 0.1, and 0. Add up these and give me the number 0.14. Now, this I hope you can see, if you know how to do this, how it's taking you to probabilistic reasoning, right? Bottom line is, if you have a Boolean formula and you have weights attached to these instantiations, and I give you a Boolean formula and I say, what's the weighted model count? Look at the satisfying assignments of that Boolean formula and add up their weights. That is like doing probabilistic reasoning. And as you'll see later, the secret to this is to take the Boolean formula and massage it symbolically and make it have some properties where this computation can be done in linear time on the size of the formula. So at the end, what's going to happen is you give me a Bayesian network, and you take it, you write one of these Boolean formulas with the right weights, and then turn this to a symbolic box to try to do weighted model counting on it. Okay, let me run through the other 2 queries quickly, and then we will take our break. So once we have sat, maj-sat, and now this is the e-maj-sat. So I'm going to do this one, and you're going to figure out the last one for me. This is e-maj-sat, which is NP to the PP complete. And now you get a sense of what this really means. This basically NP to the PP. We know what NP is. NP is intuitively try to find a solution in an exponential space, right? So is there a satisfying assignment? There is an exponential number of assignments. And the key thing about NP is that if I show you one of the assignments and I say, is this the guy you're looking for? It's easy to check, right? You just plug in the values of the variables. Okay. PP, similar, except that I want a count. But if I give you a guy and I say, is this the guy you're looking for? It's also easy to check. NP to the PP is the following. You're looking for a guy among an exponential space. But if I give you a guy and say, is this the guy you're looking for? To tell, you have to go and count. So it is NP with the PP oracle. It would be NP if PP were free, in a sense, right? And now you're going to see why. Here's what we have. We have a Boolean formula, A, B, and not C. And when you do this guy and the guy after it, you have to split your variables into a set X and a set Y. And this guy's with doing the split into the first set having the variable C and the second set having the variable AB. And here's what e-maj-sat. Is there an instantiation of the X variables under which the majority of Y instantiation is satisfying? So is there an instantiation of C under which the majority of instantiations for AB are satisfying? And the answer in this case is yes, because here it is. If you set C to true, right, how many instantiations of AB I have? 4. 3 of them are satisfying, that's a majority. I'm done. I don't even have to look at the other guy. I already found one instantiation of C under which the majority of AB are satisfying. Does that make sense? The first part is the NP. Is there a guy? Right? But if I show you a guy like C true, what do you have to do to tell? You have to count. Okay, now can you figure out the last one? We're splitting the variables, but now we're doing PP to the PP, and it's called maj-maj-sat. You can't have any more hints than that. So what's the question? The question is there a majority of X instantiations under which the majority of Y instantiations satisfying, right? Now, C, for that, because C has two instantiations, we really need two of them to have that property for this to work, right? Under C false, the majority of A, B are satisfying. Under C true, none of them actually. So the answer, therefore, is no. Right? Do we actually see what's going on? This is the abstract way of looking at these classes. And let me just make this remark. If you look at the SDP, what was it? I show you a bunch of variables. Is it worth measuring these? And you say, well, the probability that your decision will stick if you measure these is 95%. What did we, did you see the equation for that? What did we do? We looked at all possible outcomes. And for each outcome, we computed the posterior to see what is the decision. Correct? And then we added up the weights of those guys that kept the same decision. That's the double counting problem. Looking at all possible outcomes of the variables that you could observe, and then for each one of them, doing another counting problem to decide which one of them to basically add. You will get a much firmer intuition of these things, but the key thing to realize now is how nicely first these complexity classes are characterized by simple variations on of questions on Boolean formula. That's one thing. The other thing is to realize, and this is something we'll talk about later, that you can answer all of these questions efficiently on these Boolean formulas if you manage to take that Boolean formula and process it so it has certain properties, all symbolic. And the last thing is you can solve all of these probabilistic reasoning problems by reduction to questions on Boolean formulas. Right? This is a very powerful connection that we will exploit quite a bit later. All right, folks, so let's take our 10-minute break, and then we will get with the building models in the second hour.